You ever try to copy something and, well, it goes horribly wrong? You end up with this weird, uncontrollable monster? That's kind of what can happen when you try to clone a graph. It's a classic coding problem. You see it in interviews all the time, but it's more than that. It really makes you think about how data is actually connected. So today, we're going to crack this thing open. We'll figure out how to build a perfect, totally separate copy of a network, and crucially, how to do it without getting stuck in a crazy infinite loop.
All right, so here's the plan. First, we'll nail down what the mission actually is. What does it really mean to clone a graph? Then, we're going to meet the villain of this story, the dreaded infinite loop. But don't worry, we'll get the right tools to take it down. After that, we'll actually watch our solution work its magic step by step. And finally, we'll translate all that logic into some super clean code.
So, what are we actually trying to do here? Okay, think of it like this. You've got a super detailed blueprint for a house. You don't just want a photocopy of the blueprint, right? No, you want to build a whole new house. An identical one, sure, but it's got to be on its own piece of land, completely separate. That's exactly what we're doing. We're not just copying some data points. We're building a brand new, fully independent structure from the ground up.
Okay, so at the very core of our graph, we have something called a node. The easiest way to think about it is like a person on a social network. Each person has a name, we call that its value, and they've got a list of their friends, which we call their neighbors. It's these connections, these friendships between the nodes that make a graph so powerful. It's not just a bunch of dots, it's a whole interconnected web.
And this leads us to a really important difference. You've got your shallow copy and your deep copy. A shallow copy, that's like giving someone a key to your house. If they go in and, paint the walls purple, well, your walls are now purple. It affects the original. A deep copy, and this is what we're after, is like building them an identical house right next door. They can do whatever they want in their house, and yours is totally safe. We want to build that second house.
But yeah, building that second house, it's not quite as simple as it sounds. See, in a graph, the rooms can be weird. You can have doors that lead you right back into the room you just came from. And if we're not super careful with how we build this thing, we can get stuck just walking in circles forever. Okay, so just imagine this for a second. We start at node 1. We make a copy. Simple enough. Then we follow a path to its neighbor, node 2. We make a copy of node 2. Then we follow a path from node 2, and whoops, its neighbor is node 1. So our little program dutifully goes back to node 1. And what does it do? It follows the path back to node 2, which sends it back to node 1. You see the problem here, right? We are completely stuck. It's a digital cul-de-sac, and our program is just going to run forever, doing nothing.
So how do we get out of this mess? How do we break the cycle? The idea itself is actually pretty simple. We need to give our algorithm a memory. We have to teach it to recognize where it's already been so it can just say, whoa, hang on, I've already built this part. No need to do it again.
And the way we give it that memory is with this really slick, powerful combo of two tools. We need a smart search strategy and, a trusty memory bank. You put those two together and they let us navigate the entire graph, building our clone piece by piece without ever getting lost.
So our strategy is something called depth-first search, or DFS for short. Think of it like exploring a maze. You just keep taking the first path you see and go as deep as you possibly can. Only when you hit a dead end do you backtrack and try a different path. And our memory? That's going to be a hash map. This is where we'll keep a list of every single node we've already copied. It's our been there, done that list, and it's going to save us.
Okay, enough talk. Let's actually see this thing in action. We're going to walk through our algorithm step by step as it clones a simple little 4-node graph. You'll see exactly how this DFS and hashmap combo works its magic.
All right, here we go. We kick off our depth-first search at node 1. The very first thing we do is make a copy of it. We'll call it C1. And immediately, we add an entry to our map. We're telling it, hey map, the original node 1 now corresponds to this new clone, C1. Just like that, our memory is up and running.
Okay, following the path, our DFS now takes us to one of node 1's neighbors, which is node 2. First thing we do, check the map. Have we seen node 2 before? Nope, it's empty. So we create its copy, C2, and we log it in our map. You can see our memory of the new graph is starting to build up.
And now for the crucial part, the magic moment. From node 2, we follow the path to its neighbor, which is back to node 1. But this time is different. We check our map and bingo! There's an entry for node 1. Our memory kicks in, it tells us, stop! We already have a copy of this, so we don't create a new one. We just grab the one we already made, C1. And that's it. The cycle is broken. No infinite loop. Beautiful. Okay, crisis averted. So our DFS
having hit that wall, now backtracks and keeps exploring. It moves on to node 2's next neighbor, which is node 3. Quick check of the map? Nope, haven't been here before. So, you know the drill. We create a new copy, C3, and we add it to our map. And finally, the search keeps going until it hits the very last unvisited node, node 4. It's not in the map, so we create its clone, C4, and add it. And we're done. Our clone is finished. We visited every original node, made a unique copy for each one, and we've perfectly rebuilt all the connections in our brand new graph.
So the real takeaway here is that our hash map is so much more than just a visited list. It's our single source of truth. Every time our algorithm needs the clone for a specific node, it just asks the map. If it's there, great, we use it. If it's not, we create it, put it in the map for next time, and then we use it. This simple rule is what guarantees that every single node gets cloned exactly one time. No more, no less.
So now that we've seen the whole process play out visually, let's look at the actual code. And I think you're going to be surprised by just how clean and simple it looks now that you know the thinking behind it. Believe it or not, this short, recursive function is pretty much the whole solution. It takes an original node, and using the exact logic we just walked through, it builds and returns its clone, hooking it up to all of its neighbors as it goes. Let's break this down line by line.
Look how perfectly this maps to what we just did. That first line, if node in G, that's our memory check. That's the line that saves us from the infinite loop. Then cloned equals node.val, that's us actually building the new piece of our graph. G of node equals cloned, that's us putting that new piece into our memory, into the map. And finally, that recursive call, DFS of xt, that's the magic. That's the engine that drives the whole thing, sending our function off to explore all the neighbors and build out the rest of the clone.
So what's the big takeaway here? It's not just about this one problem. It's about this incredibly powerful, reusable pattern. You take a traversal algorithm, like DFS, and you pair it with a memory structure, like a hash map. This duo, this lets you explore any graph, I don't care how messy and tangled it is, without ever getting lost or redoing your work.
And you see this pattern everywhere. It's the kind of thinking behind the GPS in your phone, finding the fastest route. It's in social networks suggesting friends. It's how AI analyzes these massive, complex webs of data. So seriously, next time you're in an interview and you see a graph problem, remember this pattern. It's like a key that can unlock a whole bunch of these challenges.
So for our solution, we went deep with depth-first search, right? We explored one path all the way to the end. But what if we had gone wide? What if we used breadth-first search, exploring layer by layer? The core logic, using a map for memory, that would stay the same. But the order we build the clone in would be totally different. How do you think that would actually look? And are there times when maybe that approach would be even better? And that is how you tame the graph cloning beast. See? By combining a smart search strategy with a simple memory tool, we turned a really tricky loop-prone problem into a solution that's actually pretty elegant and efficient. Hey, thanks